Okay, in this section we're going to talk about polar coordinates. You may have experienced or some time with polar coordinates before, so this may not be new to you. But basically, polar coordinates are just another form of identifying points in the XY coordinate plane. Polar coordinates are actually helpful when you work with complicated functions or equations. So let's talk about what we're going to do to define polar coordinates. To define polar coordinates, we're going to fix an origin O, and we'll call that the pole. So that's going to be right here. That's going to be our origin there, O. And an initial ray from O. And so if you look here, right here, you'll see this ray here. I guess I should have put an arrow on it. But anyway, there's a ray right there. Now, each point P can be located by assigning a polar coordinate pair r theta. So basically this point here is r theta. So what defines where that point is located? Well, two things. One, if you take the angle that this ray extends from the x-axis, that gives us one of the characteristics of the point, theta. And then the other characteristic would be r, and r is just the length of this ray here. So r is just the length. So basically, let's say you just wanted to identify a random point using polar coordinates. So let's say you wanted to identify this point here. Well, basically, if you wanted to identify that point here, you would need to know how far that point is from the origin. So you would need to know the length of this segment from the origin to the point. And then the other thing you would need is you would need to know the angle that this line segment is from the x-axis. And so if you knew those two values, then that would identify the location of this point. So basically, the distance it is from the origin and the angle that the line that connects it to the origin subtends with the x-axis. Now, you can use some trigonometry, and I won't spend too much time talking about that because it's pretty simple. You may remember that if you have a right triangle, like here we have a right triangle, you may remember that the x distance on this right triangle is simply the hypotenuse, which in this case is r, times cosine theta. So that gives us this. And then the y distance to this point would simply be the hypotenuse, which again is r, times sine theta. And so that gives me y. And then, of course, using the Pythagorean theorem, we know that x squared plus y squared equals r squared. So that gives us another equation. So basically, we have three equations that relate the xy coordinates to the polar coordinates. X equals r cosine theta, y equals r sine theta, and x squared plus y squared equal r squared. And actually, you can use those equations to convert a point from polar coordinates to rectangular coordinates or rectangular coordinates to polar coordinates. Let's do some of that here. Okay, so right now I'm going to give you Cartesian coordinates, and we're going to convert them to polar coordinates. So let's say we have the point 5, 5. Well, first of all, we know that x squared plus y squared equals r squared. So r squared would be 5 squared plus 5 squared, which is 50. So that would mean r is the square root of 50, or 5 square root of 2. So that's r. Now, the x value, remember, is r. X must equal r cosine theta. So what I'm going to do here is I'm going to try to find theta by plugging in the known x value, which is 5, and the known r, which is 5 square root of 2. So I have 5 equal 5 square root of 2 cosine theta. And then if you divide both sides by 5 square root of 2, the 5's will cancel, and you'll just get 1 over square root of 2. And if you rationalize that, you get that cosine theta is equal to square root of 2 over 2. Now this is a common angle. So this is, well, it's a common cosine. The cosine of the angle is square root of 2 over 2. Then that would mean that the angle theta is actually 45 degrees. So from that, we can easily determine here that theta is 45 degrees, or pi over 4 radians, whichever you choose. So basically, the 0.55 in rectangular coordinates would be, the radius would be 5 square root of 2, the angle 45 degrees, or if in radians it would be 5 square root of 2, and then the angle would be pi over 4 radians. Okay, let's do another one. This one here, r squared equals 3 squared plus 4 squared. So r would be the square root of 25, which is 5. And x would equal r cosine theta. So we can put in 3 for x, and we can put in 5 for r. So we get 3/5 equal 3 equals 5 cosine theta, and then that would tell us that cosine theta is 3/5. Now this one gets a little tricky because we don't just have it memorized off the top of our head. What angle gives us a cosine of 3/5? So what you can do is you can use your inverse cosine function on a calculator, and I did it in degrees, so if you do it in radians you get a different value. So theta is the arc cosine of 3/5, and that gave me an approximate angle of 53.1 degrees. So the exact point would be 5 for r and arc cosine of 0.6 or 3/5, or 5 for r and 53.1 degrees. Now if you want to convert polar coordinates to Cartesian coordinates, it's actually pretty easy. All you have to do is, you know, x is r cosine theta and y is r sine theta. So all you have to do is put in the r and the theta in these little formulas. So x would be 5 cosine pi over 6, which would be 5 times square root of 3 over 2. And then y would be 5 times sine of pi over 6, which is 5 times a half. So that would give us the Cartesian coordinates 5 square root of 3 over 2 and 5 halves. Now let's talk about some more equations and some graphs. If we let r be fixed at a constant value, r equal a, as long as a does not equal 0, then the point r theta will actually be absolute value of a units from the origin. So as theta varies over an interval of 2 pi, then you're going to get a circle of radius a. So basically, if r is a particular length, and then theta can go, you know, all the way around, then you get a circle. So r equal 3 is actually the equation of a circle with radius 3. And now if you did r equals 6, it'd be a circle with radius 6, and r equal 5 be a circle with radius 5, and so forth. Now to get a line, you can actually get a line through the origin by choosing an angle. So if you choose an angle of theta equal pi over 4, and notice there's no oh, by the way, there's no angle given here, so the angle's allowed to go from 0, well actually it's allowed to go from 0 radians to infinity radians, you know, if you just let it keep going. And then there's no radius, so therefore this segment, this line, goes on forever and ever in each direction because r is not bounded. But it's got to go through at an angle of theta equal pi over 4. So that basically would be the line y equal x if you think about it. But anyway, it can be defined with this formula, theta equal pi over 4. And you know, like if you had theta equals 0, that would be the x-axis. If you had theta equal pi over 2, that would give you the y-axis, and then angles in between would give you different lines that go through the origin. So you can read that there. If you need to, pause the video and then read that information below there. Okay, so if we wanted to graph, let's say we wanted to graph everything where r is 1 to r is 3. Well, r equal 1 would give me a circle with radius 1, and r equal 3 would give me a circle with radius 3. Well, I want all values less than 3, so it'd be everything inside the big circle, and all values greater than or equal to 1, which would be all values outside the small circle. But I'm actually not going to graph the entire circle because I'm only going to go from theta equals 0 to pi. So really, when I say r equals 3, I'm not getting the entire circle. I'm only getting the upper half, because I'm getting that here would be r equals 3, theta equals 0, and then I would go up here to theta equal pi over 2, then I would go over here to theta equal pi. And then this would be r equal 1, theta equals 0, and then we go from 0 over to pi, and we get that. So that shaded area would represent the region that we're describing here. Now here we're talking about the line theta equal pi over 4. Now remember, up here the line went on forever and ever in both directions. But here, if we wanted to find the line to only be a certain length, only to go to a certain point, then we're going to go to the line theta equal pi over 4 from the radius of -1 to r equal 3. That would actually put me 1 unit in this direction. So since r is -1, it would be this direction. And then to r equal +3 would send me out here 3 units. So basically the distance from here to here would be 3, and the distance from here to here would be 1. But notice it subtends in the negative direction for r. And of course the angle is pi over 4. So that's one way to get a line segment. And last, let me show you this one. This one basically just lets theta range between pi over 4 and 3 pi over 4. Well, this line is pi over 4, and this line is 3 pi over 4. Now there's no restriction on r, so technically these go infinitely in this direction and these directions. So okay, and so everything less than 3 pi over 4 would be everything on this side of this. And then so actually, if you want to stay you want theta to stay between pi over 4 and 3 pi over 4. So that would be between here and here, and on the lower half it would be between here and here. So that would be the shaded area that would represent. Okay, I'm going to finish this section up with another video, but it'll be kind of short. But what I want to do is I want to show you how you can convert equations from one form to the other, from Cartesian to polar or polar to Cartesian. So I'll have to show you that on the next video.